If you were stranded on a desert island, what would you need to survive?
Physician's desk reference.
Nice, smart.
Hollowed out. Inside, waterproof matches, iodine tablets, beet seeds, protein bars, NASA blanket, and, in case I get bored, Harry Potter and the Sorcerer's Stone.
In the movie Castaway, the main character knows one crucial skill: spearfishing. But it's not as easy as it looks. The fish you see is not where the fish actually is. Light is playing a trick on you. I have an empty bowl in front of me. Now I pour in water. A coin appears. It feels like magic, but the explanation lies in refraction, the bending of light. In the previous episode, we introduced rectilinear propagation of light. Light travels in a straight line within a single homogeneous medium. But what happens when light passes from one medium into another? For example, from air into water or glass. We will investigate this through a simple experiment. Here is a fish tank filled with water. To make the light beam easier to see, I add a few drops of milk. Now I shine a beam of light from air into the water. An imaginary line drawn perpendicular to the water surface is called the normal. We also have the incident ray, the point of incidence, and the refracted ray. The angle between the incident ray and the normal is the angle of incidence, theta sub I. The angle between the refracted ray and the normal is the angle of refraction, theta sub R. The moment the light ray enters the water, the beam bends toward the normal. Refraction is the change in direction of light when it passes from one medium to another, like from air into water. When light travels from air into water or another optically denser medium, the refracted ray bends toward the normal, so the angle of refraction is smaller than the angle of incidence. As the angle of incidence increases, the angle of refraction also increases. If light strikes the surface normally, that is, straight on, perpendicular to it, its direction of propagation remains unchanged. Here I draw the incident and refracted paths on the tank. If light follows the refracted path from the water back into the air, the ray in the air travels along the original direction of the incident ray. This shows that the path of light during refraction is reversible. Now the angle of incidence and the angle of refraction trade places. In this situation, the refracted beam bends away from the normal. Light originating from a fish in water bends as it passes from water into the air. When we trace the refracted ray backward, the point appears to be at a higher position. This makes the fish appear higher than it actually is. Experienced fishers know how to aim below the apparent position to compensate for refraction. The same principle explains why a straw appears bent when partially submerged in water. 1941, after sinking the British battlecruiser the Mighty Hood, the Nazi battleship Bismarck became the prime target of the Royal Navy. The loss of the Hood, one of Britain's most iconic warships, ignited a powerful drive for revenge.
I'm always angry.
And a determination to stop the Bismarck at any cost. As the pursuit intensified, the British cruisers Norfolk and Suffolk tracked the German battleship across the North Atlantic. During the chase, the Bismarck slipped out of sight into a sea mist. Moments later, the ship suddenly reappeared, seemingly charging towards the British vessels at high speed. Alarmed, the cruisers separated, preparing for an imminent attack. Observers on both ships watched in astonishment as the Bismarck shimmered, blurred, and then faded away again. Yet radar reports showed that the Bismarck had made no change to her course. What happened? Light travels in straight lines, only in a uniform medium. When the density of the medium changes, light rays bend due to continuous refraction. This effect can produce a mirage, and that is exactly what happened during the summer pursuit of the Bismarck over the sea. In summer, the air above the sea becomes warm while the seawater remains cool. This creates a layer of cooler, denser air near the surface and warmer, less dense air above it. When light from an object below the horizon travels upward, most rays never reach the observer directly. But some rays pass through these layers of gradually changing air density, bending smoothly and curving toward the surface before finally entering the observer's eyes. When the observer traces these rays backward, distant objects appear higher, distorted, or even floating. This type of mirage is called a superior mirage. Here's a real example. Over the Baltic Sea, the distant object appears stacked into multiple upright and inverted images. Can light be bent? Let's try it.
Do or do not. There is no try.
Okay, let's do it. Pour a layer of sugar into a tank. This creates a denser layer, just like the cold, heavy air near the sea surface. Now slowly add water. Using a card helps soften the flow so the water and the sugar don't mix too quickly. As the water settles overnight, the tank forms a smooth density gradient. Dense solution at the bottom, lighter solution at the top. When we shine a horizontal laser beam through this sweet water, the beam begins to curve downward as it approaches the denser lower layers. Now I tilt the beam upward. As I gradually reduce the angle, the light bends into a smooth arc, just like the light ray bent in the previous diagram of a superior mirage. Can we see a mirage in a fish tank? This time, I place a mirror underneath the tank and I add a thin layer of sugar. Overnight, all the sugar dissolves and forms a gentle density gradient from bottom to top. When I shine a horizontal laser beam through the tank, the beam curves downward towards the bottom mirror. It reflects off the mirror, bends again into another arc, and reflects once more. Soon, a whole series of glowing arcs appears along the bottom of the tank. Now I tilt the beam upward. As I gradually reduce the angle, the beam forms arcs again, bending smoothly through the gradient. I reposition the tank and place a P-51 fighter plane at the far end, inside the tank. A Volkswagen Beetle car is lined up with it, but the car sits outside the tank. As I gradually lower my viewing angle, a stacked mirage of the P-51 appears above its real position. Multiple upright and inverted images float in layers, just like a real superior mirage over the sea. Even though the car is now completely out of my sight, the mirage of the P-51 remains visible. The bending light inside the tank allows me to see an image of the plane long after the direct view is gone. Now I slowly raise my viewing angle. The stacked P-51 mirage appears first. Then the car comes into view again. Finally, the actual image of both. Another kind of mirage appears on land, especially in deserts. It looks like there's water or a shimmering blue lake on the horizon. In a hot desert, the air near the ground becomes extremely warm, while the air higher up stays cool. This creates a layer of hot, low-density air near the surface and cooler, denser air above it. When light from distant objects or sky travels downward through these layers, it bends smoothly and curves upward before finally reaching the observer's eyes. When the observer traces these rays backward, the distant object appears upside down and lower than it really is. This type of mirage is called an inferior mirage. The sky creates an illusion of a pool of water. That's why thirsty travelers see what looks like a lake on the horizon. This has been a long episode. This is Dr. Walden. Let me leave you with one last question. Have you ever seen half of a dock swimming?